Hello, I'm Tim Holey. Welcome to the 5th session of Advanced Scientific Computing, Producing Better Code. Today, we're going to return to our core focus on Julia itself. We've had an introduction on Julia. We've had 3 process-oriented sessions, and now we're back to sort of how you leverage Julia to get the most out of it. And one of the things that attracts the largest number of people probably to Julia is the possibility of getting truly exceptional performance. And this really is possible to achieve on virtually any task that you're interested in using Julia for, if you're willing to, well, sometimes it's actually almost trivial to get fantastic performance on your code. Sometimes you have to put in some work in order to do that. And so today, the overall goal of the session is to essentially teach relative newcomers to Julia how to avoid some of the most common performance traps, because there are a few pretty common gotchas that can cause Julia to perform sort of more like this vehicle here. And, the view might be great. Hopefully you're already getting a sense that it's very elegant and pleasant to write code in Julia. And for many, many tasks, performance isn't really all that necessary, right? If it's a small amount of data or a little one-off or something like that, you may not care at all about the performance, in which case your best option is to just write the code in whatever way gets the job done. But a lot of us turn to Julia because on certain occasions we really need to get the ultimate performance. And so today's goal is to teach you how to use some of the more refined aspects of using Julia in a way to keep it from being slow, basically. So you may remember that in my first lecture, I distinguished truly fast, which are very highly optimized. They pull sort of every trick in the book, from simply being not slow. And that's really the focus of today's lecture. How do you avoid performance gotchas that would turn Julia from what can be a very fast language into a much slower language? And the good news is that Julia has very good tools for helping you discover, where things went wrong. And I'll introduce you to a couple of those tools over the course of today's session. I'm not going to ask you to just rely on tools, because as always, the most important debugging tool you have under any set of circumstances is your own ability to reason about the code, right? That is, to understand what's going on, why something might be happening. You might need to collect some data, and that's really the role of the tools. But at the end of the day, you being able to understand how Julia works well enough to understand why certain constructs are not delivering the performance that you might expect or hope that they would, is your most powerful ally in going from writing sort of mediocre Julia code to writing, world-class Julia code. And so today's lecture really it's not going to be a showcase of high performance code. It's actually going to be essentially an exploration of bad Julia code, right? It's going to be an exploration of all the ways in which one can make mistakes and mess up Julia's performance. And so our overall focus today is going to be on type inference. We're going to talk about how that interacts with methods and specialization. We'll talk about the key sort of feature in terms of how this relates to performance, which is runtime versus compile time dispatch. And then I'll introduce you to some of the tools for benchmarking and profiling. And, a lot of this actually is essentially just an elaboration of some of the things that we sort of hinted at in the very first lecture in this course. But now that you're much more comfortable with Julia, hopefully from having done all the homeworks, that it's time to dive a little bit deeper. And this is not always taught at this stage of people's development in Julia, but this is a course that's really designed to take experienced coders and just get them very good at using Julia. And so the overall goal here then is to give people who are probably learning the language quite quickly a little bit of sort of inside information into what they need to do to make their Julia code really shine. Okay, so we're going to spend most of this lecture exploring what looks like a completely trivial example, and it is from a code perspective, but we're going to look at it in sufficient depth that you're going to learn a lot about how Julia works under the hood. We're just going to create a tiny function here, add2, that takes a single argument as an input. And we imagine that X is an indexable object. It doesn't actually matter what kind of indexable object it is. Any indexable object would be good, as long as there are 2 items, and you can extract the first one with X of 1 and the second one with X of 2. And we're just going to add those 2 things together. Okay, so we'll define this function here in our session. And then we will sort of explore it with different types of input. So just to show you that things are working here, let's pass in a vector of float 64 numbers. And what you can see is that sure enough, it returns the expected value of 3. And if we just modify the input ever so slightly here, you can see it also returns mathematically the same value of 3. But you notice that the printing is different, and that reflects, as you know by this point, the fact that these are of different types, right? This is a floating point number representing 3, and this is an integer representing 3. And the fact that we defined a single method here that actually gave rise to 2 different types in the output is something that I hope you're paying attention to and noticing. So question is, what's going on under the hood that enables or that causes that to happen? Is that a good thing? Is that something we should be worried about? Under what circumstances might we ask those questions? So that's really the purpose of today, right? So first of all, let's verify that we don't have, one way you could produce multiple output types is to have multiple methods, right? So let's just check that real quick, just make sure that nothing weird happened. And Julie will tell us that sure enough, as expected, there really is only one method for add to, and we defined it. So there's nothing really surprising going on there at the level of the methods. There really is just this one bit of code is the only bit of code that is defining add to, okay? And yet it's doing different things when passed different types of inputs. Okay, well, maybe we can, let's grab this method, and Julia provides the at which macro so that you can extract the method that will be called given the types of the arguments. And so we can do that, and you can see again here, it's essentially the same printout that occurs here. But now we actually have the method stored in a variable m. And that's going to let us do some interesting analysis on it. So there's a package called method analysis, and it has a function in it called method instances. And let's take a look at what this output is. And so if you look at that output here, what you can see is it actually returns a 2-element list of so-called method instances. This is a type you probably have never encountered before. But they're pretty self-explanatory, right? This one here says that there's one method instance for add to when passed a vector of float 64s, and there's a second instance for add to when passed a vector of ints. And that is interesting, right? That actually matches what we've called this method with, right? We called it once. If we go backwards, we called it once with the vector of float 64, and we called it once with the vector of int. And so what you might hypothesize under these circumstances is that these method instances, these are instances of the method. There's only one method, but Julia itself will generate multiple instances of that method for handling different argument types, right? And so this is a form of specialization. This is a form of specialization that Julia does automatically for you. You can specialize methods. You can create methods that depend on the specific types they have, and you can have therefore multiple methods for a single function. That's a hand-generated, a manual form of specialization. This is automatic specialization that happens and is generated by the compiler. And so I'll refer to this as compiler specialization. Let's see what happens. Just to check that this model of what's going on under the hood is actually accurate, let's try passing in a novel type that we haven't before. We've seen what method instances exist. So far, it's just these 2. So we might guess that if we pass in another indexable type, this case a tuple rather than an array, a vector, then we should generate another method instance. And so here you can see it generates 3.0. It's the same output that we got when we pass in a vector of float 64. And that's because Julia, when it adds an int and a float 64, it will return a float 64. You'll see that actually in more detail. And so now let's call this method instances again. And sure enough, it's been updated. Now we have 3 method instances, and you can see that the newest method instance that's been added is for a tuple where the first element is an int and the second is a float 64. So as you can see, we added a new method instance just by calling it with a different argument type. So yeah, so these are created for you automatically. And one of the things that I should point out is that if you call this again, it doesn't add a copy of this method instance or anything like that. And in fact, all of the compilation, obviously this is a pretty simple case, but in more complicated cases, sometimes the amount of work that has to be done to compile all these different method instances can actually be take quite a long time. The good news is that Julia only does it the first time you call it. And then once it's compiled it has the code in your running session, and it will, when you call add to, it will look up and say, do I already have this code? If so, let's just run that. And so then you don't pay that compilation cost again. Okay, so what are the differences between these different? So Julia's created 3 method instances for the 3 different types of objects that we've passed into it. What are they actually? What are they under the hood? How are they related to one another? And so Julia will actually let us also see that as well. So the first way we're going to see sort of under the hood of this function here is to use the so-called Atcode lowered macro. And what this gives us actually is a representation of this specific method that is applicable. There's only one in this case, but that's true in general, that it will give it to you for the specific method. And it actually doesn't specialize it for the particular method instance. So we would get the same output from this Atcode lowered here for essentially any iterable container that we passed in here, because there is only one method, and so it should retrieve the same thing from it, right? And so if we run this and we look at the output, this is a little bit complicated. And again, as I warned you, we really are looking under the hood at how Julia actually stores and represents code internally. So it is going to look a little bit different, but I think these cases will be simple enough that they should be fairly clear. The way you can see that this works is, you may recall the way add to is implemented is it just gets x of 1 and x of 2 and then adds them together. Well, that's really what these different lines of this code info output do. The first one here is extracting the value of x at index 1. This one is extracting the value of x at index 2. These little symbols here, right? So and the key part is that this syntax here with the square brackets, that's actually implemented under the hood as simply a function call to a function that's called getIndex. And Julia, or the lowered code, shows you this base here because it's being very clear about exactly which function, which module owns the function that we're going to call, and that function is defined in base, okay? So that's kind of the meaning of these first 2 lines. Now you notice there's this assignment operation here, and those are funny looking variable names, but you can really think of them basically as temporary variables. So these are called SSA values in sort of the compiler lingo. You don't have to worry about that. Just think of these as temporary variables that it's storing the result of that get index. And then you can see on the 3rd line here, it's taking those 2 temporary variables and adding them together and storing them in a 3rd temporary variable. And then it's going to return that value there. And then the only other part of this that I really haven't explained is all these kind of markers here. These things just delimit blocks of code that run in a straight line fashion. There's no branching, there's no if or whiles or for loops inside of any block that has a single sort of chunk around it. If you look at more complicated code that does have branches in it, you'll see it's a series of those little blocks, and within each one there are no branches. So it's just a visual guide to help you understand how the code gets sort of chunked up. Okay, so this is actually what gets stored internally in Julia when you define a method. Okay. And it's in this much more sort of closer to the compiler form, but it's not really all that close yet. And the reason why is that there's really no additional specialization going on here. So we can look at now the method instances themselves by switching to a different macro. This is Atcode typed rather than Atcode lowered. And to keep things simple, I'm going to first start out by passing in this optimize equals false. This will turn off some additional optimizations that Julia's type inference engine is willing to make, and just make the simplest change, right? And so this, I should say, now represents a specific method instance, and that is effectively it's add to specialized for whatever type its arguments are. And so let's take a look at that. And what you can see, hopefully you remember that last one, I can go sort of toggle back and forth and show it to you again, is that this is really remarkably like what we just saw, but with the addition of these cyan colored type indicator. So this is a notation that means the value that comes back from this getIndex call is an int. And this one is 2. And the result from adding 2 ints together is also an int. And therefore, it knows that this overall function calls an int. So just to sort of make it easier to see, let me toggle back to this code lowered, right? And what you see is that it's really is identical, except that all we do is we're adding type annotation. Okay, so we have now this code has been annotated, and this is only true for this specific method instance that's relevant for when you're passing in a vector of ints, right? That Julia knows, has figured out somehow that this first operation returns an int, the second one returns an int, the third one returns an int, and it knows the overall function returns an int. If we do the same thing with a float 64, you can see that Julia knows everything in this is a float 64. So that's really quite nice. Let's look at the case now of a mixed input where the first one is an int and the second one is a float 64. And again, you can see that it knows the first one is an int, the second one is a float 64, and it knows that the result of adding those two numbers together gives you a float 64 and returns that. Okay, so we've been able to really figure out what we're really seeing essentially is the code for the 3 separate method instances that get generated. It's really all the same set of calls that are being made in this unoptimized version of the code, but Julia knows that the types are going to be different, and that type information gets stored with the method instance. So how does Julia know all of this? Well, this is this phenomenon of type inference, where Julia figures out when you pass in arguments of known type to a function, Julia will try to figure out what type of objects it will return. And so what you have to start from is what are the types of the input. So in this case, it's a vector of ints, right? And then remember that the very first line was a call to getIndex. We can actually sort of effectively dive into that version, to that function also, and you can see it's implemented through a lower level call, this base.arrayref, right? And then you remember that the only other call in this function was plus, right? And so let's look at the implementation of plus. And when passed, again, we're using code typed here, not code lowered, right? And when you pass 2 ints to a plus, it calls a function, it turns out, called base.addInt. This int is for adding integers. And so Julia knows that this is an int. Now, you might imagine that this process continues, and most of the time it really does. This might call other functions, which might call other functions, which might call other functions, but eventually you do have to get down to the bottom. And Julia is built on top of a set of very primitive operations that are essentially built in, right? So we've already hit one of these with this addInt function here. If we try code typed on this, Julia will give us an error. And you can see the error says the argument is not a generic function. So the issue basically is that addInt is one of these primitives that's built into Julia. The non-primitives are called, or the primitives are called built-ins. Non-primitives are generic functions. And so we can't introspect any further into addInt because it's one of the sort of 80 or so primitives that Julia is built on. We can look to see how something else, a different addition operation, one's a little more complicated because we're passing in 2 separate types here. And what you can see here is the way that Julia implements this is it first promotes the 2 different types to the same type, and then it calls plus on them. Now, this is a little bit complicated. This is essentially the same syntax that's used for a variable argument, meaning where you would potentially have multiple arguments passed to the same function. You might imagine that's a little bit inefficient, but no fears. Julia knows how to optimize things. And to show you that, we're going to actually finally turn on this optimization feature of code typed. And what you see in this circumstance is that what happens is that Julia will first convert the signed integer to a floating point number. And so it converts the int to float 64, and then it adds 2 float 64s. So right, y is already a float 64. Here it's stored in a temporary variable, the float 64 version of that int, and then we just add them together and we're off to the races. Okay, so this really has allowed us, but yet these individual things here are also primitives built into Julia, it turns out. Now, it's actually possible to go even deeper than this. This is not the last stage that Julia lets you see the representation of code. So it turns out that what Julia does after this point is it actually now converts code that looks like this highly optimized version of it into a format to interact with a compiler called LLVM. And then LLVM is responsible for generating the final version of the code, which is the native CPU instructions that are optimized for your particular CPU on your machine, right? And so you can look at those if you're interested. I'm not going to show them as part of this lecture because they do get more complicated and even less familiar in terms of their representation if you've not used to looking at those particular representations. And very often this is as far as you need to go to diagnose problems in terms of the performance of your Julia code. So we've actually learned a lot about how Julia works under the hood. So first of all, so backing up a step, when you write code, of course, you're just writing text files, right? So those text files can get read in as a string effectively. And what happens when you then what happens is Julia will parse that string into what are called expressions. It's a type called expr in Julia. And this is essentially just a representation, a structured representation of the code you wrote. It does things like matching the parenthesis in function calls so that you don't have to do that at the level of raw strings. It packs it into sort of organized structures that you can manipulate. And then the next step is that those expressions then get lowered to this lowered representation. And that's what we saw with Atcode lowered, right? And just to sort of relate this to things you probably have seen before, probably by this point in your Julia usage, you're very familiar with seeing this message when you update a package or install a new one. You'll see this, pre-compiling message, right? And most of what's happening actually is this right here, right? Julia is just parsing the text files into expressions and then lowering them. And then Julia saves the lowered code to a file on your hard drive so that it can save that work the next time you restart Julia. Now, under some circumstances where the developer of a package has asked for additional information to be stored, there is a little more information stored into those pre-compile files. But probably for the majority of packages, this is most of what's happening. And so then, whether let's say when you use a package, it loads that cached file, that file that has all the lowered code stored in it. And whenever you make a function call, either if you've already compiled it, Julia will have that in its memory and it will look it up and then just run it. Or if you've never called it before with that particular combination of argument types, then Julia will perform type inference for the specific types of arguments that you're passing in. That type inferred code gets optimized. So this is like the optimize equals false stage of code typed. This is like the optimize true. It's an additional step of optimization that happens. And then the result gets compiled by LLVM. And then finally, Julia will run the compiled code. And then so the next time you just go straight to here, which is basically the same step as this one here, right? Okay. So that's an overview of Julia's sort of overall pipeline of how it works under the hood. Now, this has very important implications, right, for your performance. And that's the main reason that I've kind of dragged you through these internals of Julia so that you can appreciate the importance of types to Julia's performance. So first of all, remember we defined add to this way. However, this leaves an important question open, and that we can see what that question is. You may have already sort of made some guesses that this might happen. What is this plus here? Well, this is actually a function call, right? We're just calling the plus function. And plus has a lot of methods. There are 190 separate methods for plus available, right? So the question is, how does Julia know which of these methods is the right one? Right? Well, the way it knows is that it chooses the most specific method that is applicable for the types of the argument. So in this case, the types of the arguments are x of 1 and x of 2, right? It's equivalent to, we could have written this, in the following, I guess this is in Markdown, but I'll just edit it here. So we could have written this function definition here, and it would be then more apparent that this is a function call by the plus function. Right, and so it has to pick which of but it has 190 separate methods in our current Julia session, more maybe if we loaded some additional packages. And so, this is really a lot of methods to have to figure out which is the magical one that is the applicable one for the specific types of X1 and X2, okay? And so the key question is which of these methods gets called? And, you can see the decision process basically again from this Atcode typed. Here's a circumstance in which we know that the first argument is an int, and we know that the second argument is an int. Since it knows that, since in this typed code, Julia knows the types of the two arguments, it can, while compiling this code, figure out which method is the one that's applicable for those two types. So it didn't have to run the code to figure that out, right? That's because this type inference, Julia can essentially peer into the future. When I run this code, what types will %1 and %2 be? And if I know those types with certainty, then I can figure out which method will be applicable to them at the time I'm building the code, not at the time I'm running it. I already essentially look up that information when I'm compiling the code, not when I'm running it. And this is really Julia's main performance bit of magic, basically. And you can see this just simply by running this instead of with optimize equals false. Oh, sorry. Optimize equals false right here. You can see the result of having figured out which method is going to be called in the optimize equals true. Now, that's not always the case that it will paste. What it's going to do now is an optimization called inlining. It's basically pasting the code for plus into this method body, basically, right? And so here you can see, again, it's extracting the first two items, and then it's going to convert that integer into a float 64 and then add the two floats together, right? So what it's effectively done is pasted the code for plus into the body of this method. And that's because it's a very simple function, and Julia will do that. It doesn't always. Sometimes it leaves it outlined, so to speak, so that it's a regular call. But for very short, quick things, it makes Julia much faster to do that. And so you can see that inlining step here with this optimize equals true. Okay, so this is only possible if Julia knows exactly which method is going to be called for this particular method instance, right? Which method of plus is going to be called for this particular method instance. And so this ability to peer into the future, guess the types of the arguments, and then look up the functions ahead of time is, again, a key component. So this is called compile time dispatch, right? So meaning the dispatch, meaning the choosing which method will get executed, happens when the calling function, when the function you're running is being compiled. The alternative to compile time dispatch is sometimes called runtime dispatch. And we can see that too, even with this very same function without ever defining a new function. And what we're going to do instead in this case is we're going to defeat the ability of Julia's type inference engine, deliberately defeat the ability of Julia's type inference engine to work by creating a vector that contains no information about the types of the objects stored in it. So those others were like a vector of int, a vector of float 64. This is going to create a vector of any, right? And what that means is literally any kind of object. It might be a string, it might be a dictionary, it might be an image, it could be anything you want, right? Might be stored in the slots of this vector here, right? So under those circumstances, Julia cannot predict the types of the objects that will be extracted from that vector. And therefore, even though we've turned on optimize equals true, and you would hope that Julia would do all the kinds of inlining and stuff like that, there's nothing to inline because it has no clue what method of plus will be applicable under this circumstance. You can see the first object is inferred to be of type any. That basically means Julia has no idea what type it is. And the second type is inferred to be a type any, and then therefore the result of plus is also any. If it doesn't know what the inputs are going to be, it can't figure out what the output is going to be, right? And so Julia knows very, very little here, and it's not made any substantive progress on optimizing your code for this particular case, right? So this then would have to be executed via what's called runtime dispatch, right? So, it knows that this array ref is going to be called. That's progress of a form, but it doesn't know what the result will be. It does, and the reason it knows what method will be called here is because vector of any is a type that Julia understands, right? So that part is a so-called concrete type. It can figure out which what's going to be called here, but it doesn't know what the result will be, right? But then but the really sort of the key decision has to be made when it goes to call this plus operation, because here it has no ability to predict in advance which of those 190 methods, other than maybe ones that have different numbers of arguments, right? A one argument version of plus, which just simply returns the object under any typical circumstance, that's not applicable because this has two arguments. But that's about the only piece of information Julia has to go on, right? And so it doesn't get very far. And so what this means is then that this method will be looked up and called when the function is running. And so this is called runtime dispatch, right? And so, a schematic of what runtime and compile time dispatch look like might be like this. It's basically, if you think of a compiled function as a blob of native code that's living in a particular memory location, when you're down at the very lowest levels of the machine, the calling a function involves sort of getting the arguments ready to be passed in, and then deciding which specific compiled blob to call. And the analogy is like, this is kind of like looking up somebody's phone number in the phone book. You may not know which page the person's phone number is on, and which column or whatever, in the sort of old days where people used paper-based phone books. And so it may take you some time flipping through the pages, trying to find the right name to then look up the phone number. Right? And so when you're doing a compile time call, it's very fast. All you do is get the arguments ready to go, and then you transfer execution to the blob of compiled code. Super, super fast. When you're doing a runtime call, the very first thing that has to happen is you have to figure out which blob you're going to get for the types of the arguments. This happens during the running of the function. And then from there on, it looks a lot like this, basically, right? And so, but it's this lookup process, the process of paging through the method tables, trying to figure out which one is going to be applicable to this particular set of arguments, is the slow process. Okay, so let's actually measure some of this. Let's see whether is this really that big of a deal or not. And so what I'm going to do here is we're going to measure the performance of this function. Now, Julia comes with a built-in @time macro, and that's very handy for some things, but it's not handy for very fast-running functions. And this is a very fast-running function. So we need something that goes to a little more effort to benchmark things with a little greater care. There's a lovely package called Benchmark Tools. I highly recommend using it for any fast to run, anything that's less than even a few milliseconds, or sometimes often even tens of milliseconds. I would recommend using Benchmark Tools for. And so it has this @btime macro. And if we run this here, so we're loading the Benchmark Tools package, you can see that this runs in just 1.5 nanoseconds. It's very, very fast indeed, right? Oh, and I should say, I want to show you that there is a gotcha in using Benchmark Tools. Sorry, this is the fixed version of it. So the original here, if you just do this naively, you might get a result that should surprise you. And that's what I wanted to caution you about. This is a fraction of a nanosecond. This is unrealistically fast, right? So computers have so-called CPU clocks, and those CPU clocks usually tick a few times per nanosecond. And that each tick basically is, roughly speaking, one or a few operations. Is actually substantially more complicated than that. So I'm grossly oversimplifying. But the fundamental reality is that if you measure times that are grossly less than a single CPU clock cycle, that is not plausible. So if it sometimes, if even a large percentage of a nanosecond might be plausible, not usually in a single item benchmark process like this, but anything this tiny is just not believable. So what this is an indication of is that Julia's compilation engine is so clever that not only did it figure out all the types ahead of time, it actually figured out the value that it was going to return from this function. And so it replaces the entire function call with a constant value of 3.0, right? That's a little too smart. We actually want to, for the purposes of measuring performance here, defeat some of that optimization. And so there's a Benchmark Tools has a very nice trick for that. And that is you can run setup code. And so what I'm going to do here is generate a random integer between 1 and 5 for x and a random floating point number for y. And because these are not predictable from run to run in their value, Julia can't anymore substitute the actual result of the computation, right? It'll be different each time we run it. And so now you get the actual true story, right? So it's a much, a much more realistic amount of time for a function like this. Okay, so this shows you that, this gives you a sense of the performance here under these circumstances. Here, this is for a tuple. Let's also do it for an array. And again, you have to remember that not only in this case are we using random numbers to defeat any kind of compile specialization, but also actually array creation takes some time. And if you don't want to incorporate that into your benchmarking, it's better to put that in as part of the setup code, right? And so again, here you can see very, very nice fast execution under these circumstances, right? Now let's contrast that with, so just switching from a tuple to array is not a big deal. Here we're going to switch to an array of any, okay? And this is going to be bad because in this circumstance, now suddenly you can see we're well over 20 nanoseconds. This is, an order, more than an order of magnitude slower than this code here. And all this comes from the fact that Julia has to do that method lookup at runtime rather than compile time. Okay, so it's useful actually to keep in your head what the sort of ballpark costs of these operations are, because it can help you reason about your code in important ways, right? It's worth knowing, that the cost of a single runtime dispatch for a single argument is typically around 15 or so nanoseconds. It can be a little bigger than that under some circumstances, and of course it depends on your specific, hardware, right? That's true for mine. If you have more arguments than that, it can grow pretty rapidly in terms of how long it takes to do runtime dispatch. So it really adds up. Now, whether this is something that is trivial and you shouldn't worry about it at all, or catastrophic, depends entirely on what you're doing. If this is one operation that will happen once over the course of your computation, you are never going to notice 15 nanoseconds being wasted, right? Completely, utterly irrelevant. But if this is in the inner loop of some computation that you're running billions of times, this could be a huge deal, right? If you do this a billion times, that's 15 seconds already right there. And there are many circumstances where an operation may start out taking a large fraction of a minute, and after a few optimizations, it's a tiny fraction of a second, right? And so, eliminating runtime dispatch is the single, I would say, for Julia newcomers, is the single most common thing they can do to improve their code, basically. All right. The one last point I want to make, and this is partly just to sort of illustrate that I'm not cheating by creating an array that has two different types in it, and that's not the source of the problem. I want to show you, but I also want to show you this is one way to work around cases where you do need to be able to accommodate heterogeneous types, but you don't want to pay the full price of runtime dispatch. Julia is so excited to do method lookup at compile time that if it knows that there's only a very small list of types that might be applicable, it will still do all the method lookup at compile time. And that's called union splitting. And basically what it does is it will insert a branch in your code and check what the type of each element is. But since there's only a limited number of possibilities, it can look everything up ahead of time. So in this case here, we're creating an array where the elements can either be a float 32 or a float 64. They're not any anymore, so they're not completely unknown. Julia knows with certainty that they are either a float 32 or a float 64. And under this circumstance, you can see it's worse performance than what we got before, but it's a heck of a lot better than the untyped performance that we got, right? And that's really because with union splitting, what we typically then get are, bits of code that look like this, where basically Julia will check to see what type of the argument is, and then it will use one compiled blob. And if it's the other type, then it will use the other compiled blob. So these, importantly, are not being, there's nothing in this that's being looked up. There are no blobs being looked up at runtime. The compiler looked them up ahead of time. It just doesn't know which one's going to be applicable, right? But it can check that at runtime. But especially if these types are concrete types, meaning there is only one such type that fits that description, it's not an abstract type that you could subtype, then this comparison will also be exceptionally fast, right? And so you'll get very good performance under such circumstances. Okay, so that, I think, arms you with the understanding of Julia's internals you need in order to write good code. Now, even experienced Julia developers sometimes unknowingly write code in a manner that breaks type inference. I think this is a fairly common observation. And so when you're writing code whose performance you care about, the key thing to do, once you've got it written and working, and of course, getting it working and working correctly, producing accurate outputs of the types that and values that you expect it to, that's certainly your first step. But once you get that working, then you might want to start tuning the performance of your code a little bit. And parenthetically, I'll point out, now that you know all about Git, it's very good to make commits at different stages. Once you get it working, of course, you want to make a commit, because you can always then go back to that spot, right? But then once you've got things working, you want to figure out where it's spending its time. And certainly what we've been doing so far is just timing the execution. And that's very informative. We've learned a lot, I think, by looking at the execution time. But as code gets more complicated, just simply measuring the aggregate time that it takes to run becomes less and less useful, because then you have to start guessing, okay, which part of my code is eating up all that time? And what I encourage you to do under those circumstances is to use a set of tools called profilers. And so that's one of the major topics for the remainder of this lecture, is to introduce you to some of these other tools. We talked about Atcode types and other things like that can give you insight about the types in your code. Now we'll look at profiling as another way to get a really big picture view of what parts of your code are taking up the time. And in very rough terms, there are two types of profilers out there. Profiler, it would be the name of the tool. So-called instrumenting profiles, they add measurement, so-called instrumentation, to your source code. So let's say that your source code looks kind of like this, right? So on line 17 of your code, you call f on x and store the result in y, and then on line 18, you call g of x and y and return z. And when you run this code under an instrumenting profiler, it will actually modify that code effectively and run it code that looks like this. So basically, it has some sort of buffer where it's keeping track of timing data. And right before it runs this first line here, it might basically record some information about where it is in your source code and what the current time is, right? And then it will make that call. And then after it finishes that, it pushes updated information about where it is. So now it's moved on to the next line, and it wants to, of course, know what time it is. And so it's going to query the system clock, right? Each and every time. These will all return different times, because time will have advanced, because of this function call, most likely, right? And so it'll do that again, and it just does that in between essentially every execution that gets called. Now, this seems like a very nice, very direct way of measuring time, and there are quite a few measuring performance. There are quite a few profilers that work this way. However, these instrumenting profiles, I think it's come to be appreciated, they have quite a few disadvantages. One that might be fairly obvious is that instrumentation will slow your code down, right? If you're having to store extra data between every single function call you make, then of course that may slow your code down some, right? More subtly, the instrumentation can actually essentially change the nature of the code that's executing. So the problem is that a good compiler will optimize your code in ways that sometimes change the order of operations to make it more efficient. So it may be a little different in how it's executing it than the way you wrote it. Now, compilers will typically, if it's a good, accurate compiler, it will only perform those kinds of transformations if it can prove it doesn't change the outcome, right? And the problem is that if you're recording the time between operations, the compiler will realize that if it reordered any of these operations, it's not going to give you an accurate assessment of what the time was before each operation. And so the compiler won't perform those optimizations. And so in some cases, the running code with instrumentation is really very different code than the code that runs without the instrumentation. And so you're getting actually a misleading picture under those circumstances of where your code would be spending its time in the real world, right? And there, a final problem is, it's handleable, but just any time you want to recurse and do instrumentation inside of a function call that has instrumentation around it, it gets a little complicated to subtract out the cost of the instrumentation itself, right? So, so for that reason, I think much of the world has moved on to a different style of profiler, and that's called a sampling profiler. And what happens there is that it will periodically interrupt your code and collect, program location data about where you are. So an analogy for how these are more subtle. They're not nearly as intuitive, I think, for many people when they first learn about them. But an analogy might be, suppose that you spend 8 hours a day at work and an hour a day at the gym, and you have a friend who just happens to text you at random times throughout the day. No pattern whatsoever. And just text you the single line, where are you? Meaning, where are you now, right? And so you reply, and this friend of yours does this hundreds of times over the course of a month, right? So if this person then at the end of the month just simply aggregates all the responses that they received over the course of that month and counted them up, then we can look at a histogram of them here. So I'm going to sort of plot this here. It's going to pre-compile, so this is going to be a little bit slow. But what we're going to do basically is we're going to generate a certain amount of random data, 1,000. Let's say that there were 1,000 times your friend texted you, basically, right? And then 8 times out of 9, you reply that you were at work, and on the 9th time, maybe you go to work right after, or you go to the gym right after work, then you're going to respond to the gym, right? And so we're just generating a long vector that are either work or gym, the 2 strings, right? And then we histogram them. And here's a plot of the histogram. And so here you can see, there were sometimes you responded that you were at the gym, but a lot more of the time you responded you were at work, right? And that's just because the person's asking you at random times. You're at work about 8 times as long as you are at the gym, and therefore about 8 times as many of these location queries will result in saying I'm at work compared to saying I'm at the gym, right? And so from this measured data alone, without knowing anything else, without knowing the order in which your execution happened in your code or anything else, your friend can infer that you spend about 8 times as much time at work as at the gym. And when you're going back more to a sort of a code framework, knowing where your code spends its time is the key thing you need to know about what parts of it need optimization, right? And so you can learn everything you really need to know, basically, in terms of where this code is expensive from this kind of data. So there are some, so these sampling profilers do have disadvantages, right? There are some disadvantages. One of them is you don't really get exhaustive information from them, right? Suppose that you spend at some point during this month 5 minutes at the bank, right? The odds are very slim that your friend will happen to text you right in the middle of that 5-minute period, right? So your code may be doing a few things that you don't even see with the sampling profiler. But it's a tiny fraction of the total execution time. Maybe you don't really care. From the standpoint of code optimization, you probably don't. You probably shouldn't, right? The other issue with sampling profilers is it actually is subject to sampling noise. So you do actually have an uncertainty. So if you have n counts, the uncertainty is about square root of n. So meaning if you run the same profile again and look at the results, then in fact, you'll get different number of counts for each place in your code than you got the first time, right? So there is some variability there. These are genuinely disadvantages of sampling profilers. But the huge, huge advantage of a sampling profiler is that you're running the unmodified code. And so what that means is, first of all, of course, it runs much faster, at native speeds, basically, right? It can slow down if you ask the code where it is often enough. But if you do that relatively rarely, then it doesn't really slow it down appreciably. And then that code also, of course, therefore has all of the actual real world optimizations that the compiler can do to it. So you're looking at the real thing, the stuff that runs under real circumstances and not some artifactually de-optimized version of your code only for the purposes of collecting timing data. And so even though there are disadvantages of sampling profilers, this one advantage is so huge that I strongly recommend that pretty much any time you try to profile code, that you use a sampling profiler rather than an instrumenting profiler. There are times where you have a very targeted question about a tiny block of code, and then there are actually some very nice instrumenting profilers available for Julia and other languages as well. But kind of your go-to, what do you use by default? I think many people, maybe not everyone, but many people would agree that the sampling profiler is probably the way to go there. So let's actually take a look at how all of this works. And so here I'm going to profile some code that has some. Your code needs to take a certain amount of time for you to profile it. I could fake that with just calling sleep. Sleep is actually a little complicated if you're brand new to profiling Julia's code, because it involves the sort of task infrastructure and all. And so what I'm going to do is I'm instead going to just use a delay function here that I'm calling busy wait, and all it does is it does a loop and then executes. Now I don't actually need anything of value out from the loop. This is written much more complicated than just creating a loop. And it's again because Julia's compiler is so smart that if it sees a loop that literally does nothing, it will just skip the loop altogether because it's not actually changing the outcome of our code, right? So in this case, we actually want to slow it down. And so I'm making the loop do a little bit of work and then returning the value just to make sure that Julia doesn't realize that it even though it's computing something, if you don't use the value from it, it's still not necessary. So I'm going to create this busy wait function, and we can check to see if it's reasonably accurate. It really comes down to how many iterations do we do. And so I'm going to aim here for 0.8 second delay. I'm not going to hit it exactly, but okay. So the zoom penalty is substantial here. It's worse than when I was running this without zoom, but we're kind of in the ballpark of a second-ish or so. We're not off by too much. We're just going to run with that here. And so now I'm going to mimic that texting experiment that we did with your friend, right? So I'm going to iterate through, many typical days, right? So, and on each day I go to the work for some amount of time, and then I go to the gym for some amount of time. And again, all this stuff with X is really just to keep Julia's compiler from getting rid of the busy wait, right? That's the only purpose of the X. Although what I'm really doing is just iterating n times and calling work and gym, right? And when I'm in work, I wait for 80 milliseconds, approximately, not very accurately. And when I'm at the gym, I wait for approximately 10 milliseconds, okay? So let's define all of these. And we're going to run it once to compile it. If you don't do that, you actually see Julia's type inference. You're profiling Julia's type inference, and that can be interesting. But in general, it's not what you're after for this kind of thing. And so it's usually better to run it first. So then, in order to profile with a sampling profiler, Julia comes built in with this profile library, and so we're going to load the library. We're going to clear, it has an internal buffer. We're going to clear it. You don't really have to do that on the first call, but in case I decide to rerun this, I wanted to put this in here, right? So otherwise you just aggregate the results from multiple runs of the profiler, accumulate them together basically. And so here we profiled it, and so we ran it for the equivalent of a month of time, basically, right? And worth of milliseconds. And this is we collected the data. So now let's take a look at the data. And so I'm going to first show it to you in text format. And so we're going to print it out. Maybe the simplest representation is the so-called flat format, and it's just a listing of different lines in your code that took time. So what this count section here is it's the number of sort of snapshots of your running code that were taken while you were inside of that given line. And that might represent either that function directly or one of the things it's calling, right? So that's important to realize. The overhead is when that function itself is actually doing the work, right? And so that's a more sort of direct look at the at how much work was going on inside of a given function. And what you can see here, right, is sort of so we collected essentially 41 sort of or is an overhead of 41 from running well, let's see here. Actually, sorry, the overall count in Gym itself was 334. This is specific to Gym and not the busy wait, but this actually, for our purposes, since we're not really interested in timing busy wait, this is the relevant number, right? So, and then when we were at work, we can look it up in about 2,600 here. Okay, so this is in the ballpark of about 8. This is in the ballpark of about 8 times this one, right? And so that's consistent with the fact that it takes about 8 times longer, right? Again, remember there's noise when you run a sampling profiler. Okay, so you can see that it collected almost 3,000 snapshots over the time that code ran, right? So another way, and this is actually the default way that information prints, is in tree format. And when tree format, you can see who calls who, basically, right? So from this, you can see that my days passed in with this how many days do we want to iterate argument, calls work, which calls busy wait. And then a later line in my days calls Gym, which then also calls busy work. And the indentation here encodes who called who. And you can see here the overhead, printed along with the total counts. So it's the same, roughly the same information as before, but it's attributed in this case now to the entire call sequence and not just aggregated at all the times it's spent in that particular line of code. And sometimes that's very useful because sometimes then you can see the actual way which sometimes the same bit of code gets used in many different places in your code, but it doesn't always end up taking the same amount of time. So that's very nice, and it's very useful directly. But what's often even nicer is to actually visualize your profile data. And so there are a number of packages that make that possible. And so here's one that we'll use here in this Jupyter Notebook environment called Profile SVG. This is a great choice here for a Jupyter Notebook. For any other circumstance, or I think I would actually recommend doing most of your profile of your sort of performance tuning in a different environment, simply because a package that provides much more information and insight about it is actually called ProfileView. These are sort of sister packages in a way, but this provides more interactive tools for sort of clicking on various bars and having it take you to the line of code, or all that kind of stuff. So, but here, this graph that you see here in this Jupyter Notebook, this is revealing is another representation of the exact same data that we saw in text format. And I know the fonts here are probably a little bit small, but what you can see basically is that here's line 4 of my days. This one is cut off a little bit, but it's line 5. And so this bar here corresponds to that one line of code. Sitting on top of it is another bar of essentially the same width that's inside of work, okay? And so what the vertical axis here represents who called who. So one's at the base, and a lot of these are Julia's internals that are running our session that allow us to type things and evaluate what we type. That's what this eval here is. This is evaluating the very command that we typed to run my days, right? And then this is really where the business starts. And you can see then here that, there's this my days called work, which called busy wait, which then called plus, right? And that's the thing we use to slow down busy wait, basically make it actually run. Whereas here, this this line in my days called Jim, which called busy wait, which called plus, right? And because they're waiting for different amounts of time, they take different amounts of time. So as you might guess, while the vertical axis represents who calls who, it's kind of like that tree representation. The horizontal axis is proportional to the number of samples that were collected in that function. And so what you can see right here is that, you know, the work takes a much longer time than Jim because it's a much wider bar. And so the nice thing about this so-called flame graph representation, and if you look at much more complicated bits of code, it'll start evoking more of a set of logs with flames rising above them. You can see that the visual representation really helps draw your attention to the most important things that may be worth your attention optimizing. They would be the widest bars in general, right? And the ones that are actually taking the work are sitting on top of ones that are below them, right? So that in a flame graph, the height encodes the call depth. Sometimes you see flame graphs reversed, and so the callers are on top and callees below. For these packages, it goes upward. And then the width is proportional to the runtime. That's kind of a universal of all of them. And so let's take a look at performance profiling in action here. I'm going to create a function. And so this is just to illustrate how you can use performance data to help you optimize your code. And this is looking ahead a little bit to our next lecture, which is going to focus on different topics that are relevant for performance. But we're going to discover here this opportunity for optimization via profiling. So what we're going to do is we're going to create a function. I'm going to call it mult and pass in two matrices, A and B, and a vector X. So you can see them being created down here. And in this implementation of the function here, first we multiply the two matrices, and then we multiply the matrix times the vector, right? And so again, we define the function, we define the variables input, we call it once so that we do all the type inference and compilation, get that out of the way before we start measuring performance data. We can measure the amount of time that this function, because this runs for a fairly long period of time, at time is perfectly reasonable in this circumstance, right? So we can see it created, there are a number of allocations. This may be slightly an artifact. Yeah, this is more realistic, just for maybe the first time I've called at time here. So yeah, this is more realistic of the number of allocations that were created. Now what we're going to do is we're going to actually now look at the profiling, and we can both collect profile data and view it in once with this @ProfView. And what you can see here, this is a little complicated to interpret, but if you know what to look for, it's revealing this MM stands for matrix multiply, and this MV stands for matrix vector multiply. And so you can see most of the time is spent multiplying those two matrices, just going back to how this is implemented. There's a matrix multiplication, and now a matrix vector multiplication. And you can see most of the time is spent on the matrix multiplication. And so the profile, the width of these bars attracts your attention. The fact that's your bottleneck in your code. Could you maybe get rid of that? Now, this isn't a case where we've written any of the code badly, except in one sense. Maybe what we've done is we've not chosen the best order of operations here. So instead of multiplying the two matrices and then multiplying them by the vector, what if we actually do the matrix vector multiplication first, and then do a second matrix vector multiplication? And let's see if that's any better. And so I'm going to call this mult2 so we can compare it. We're going to check first that it gives effectively the same output. This is an approximately equals rather than checking they're exactly equal, because with floating point numbers, the order in which you do multiplications actually matters in the sense of round off error. But this is tiny, 1 part in 10 to the 16th or so. So these are relatively small errors, and so to a very high degree of precision, these two are equal to each other. Now, if we time mult2, now you can see, oh my gosh, before we were at around 1/3 of a second, and now we're at such a small amount of time that you can't even trust time to measure times that are that short, right? So we've made a dramatic improvement in the performance for code by noticing that the bottleneck was, here in this matrix multiplication. We'll talk in the next session about why this is a much better ordering of operations in the for this particular computation than this one. But profiling directed our attention to this issue in our code, helped us understand what's going on under the hood. We saw those gem instead of gem Vs, and that gave us enough insight to figure out how to fix this code, basically. Okay. The other final thing I want to cover is the fact that you can use profiling to detect some of these gotchas that I mentioned at the beginning, right? So you may recall that at the beginning of the session, we talked about how add2 is fine if you pass a vector of a concrete type here. If we measure the performance with a vector of float64 or ints, it's blazingly fast. And if we measure the time with a vector of any, it's comparatively incredibly slow, right? Now, the question is, what if you do this by accident, right? So we set this up deliberately as a problem in the code, but what if you do it by accident? And believe me, it happens, right? Sometimes you'll write code and you'll be surprised that you've done something to sort of break type inference, right? And so you might need to figure out what's going on. Well, the benchmark tools package has a nice tool called @bprofile. And what this does basically is run your code, your fast running code many, many, many times while profiling it. And so it's a convenient way to collect profile data on code that runs very, very quickly, right? And you can see it gives you this kind of fancy output. This is actually a histogram of the run times of the 10,000 samples that it collected. So you can see the large majority of them were sort of clustered here right around 17 nanoseconds or so. And now if we look at this, we see something that we hadn't really noticed that much before. And that is that a couple of, or I haven't called your attention to before, and that is that some of these bars have special coloration. I want to first and foremost direct your attention to these red bars. This is the most serious thing to look at in one of these ProfileView, Profile SVG displays, and that is that it uses red to indicate runtime dispatch, right? And so what you can see here, right, is that this, that there's a fairly wide bar in add2, and it's colored red. And then remember that anything it calls is on top of it, but the colors don't add up to the full runtime of add2, right? They're in fact a tiny fraction of the runtime of add2, the callees, right? The things it calls, which in this case is get index from the array and plus, right? So the amount of time that you can account for in add2 of extracting values from the array and adding them together is a vanishingly small fraction of the overall time that add2 runs for. And the reason why all that extra time is the time that Julia is using to look up which methods are applicable, right? So this is a clear indication, since you have a wide red bar sitting on top, right? The things on the top are the things that are actually taking the time. You have some red bars down here too. Those indicate that Julia can't predict the types here, right? But when you're evaluating code typed at the REPL, that's expected, right? And it's not slowing you down because there's a bar sitting on top of it that is well inferred, and there's no problems there. This one also, again, same thing, right? But it's really when you see these red bars at the top of the flames that you start getting really worried, okay? So this is a clear indication that you have an inference problem in your code that you should try, that if you can. There are circumstances where you just have to live with inference problems when you can't predict anything. But ideally, those are buried someplace in your code that aren't then runtime performance sensitive. In this case, it is, and that it's the main thing that's holding you back. There's a second key color here. It's actually in general one that I'd recommend paying attention to second, not first, right? Because these often go away if you fix these. But this orange indicates a phenomenon called garbage collection, or it's just essentially cleaning up old memory that's not used anymore. And one thing to know about these is that these can be very variable from run to run. If I go back and I rerun my data collection, so @bprofile will actually clear the buffer, so I can just run it again. And I don't know what the outcome is going to be. Again, it's highly variable from run to run, but let's try it again. You can see it's a little different. It took up a little less of the time. There are times where if Julia had almost no garbage going into it, it might actually take up a pretty small fraction of the total time. So these will vary widely, but their width is essentially in part dependent on just how much garbage has accumulated. And that might be calls that had happened before you started profiling in some cases, right? So The need to collect garbage is coupled to allocation of memory. And so if you see a lot of orange bars, these are often pegged at sites that themselves allocate memory. It's not so clear in this case, but if your code creates even well-typed arrays, for example, those require memory allocation, and you might get at those very same sites garbage collection. And so these are at least here to draw your attention to the fact that you happen to be allocating memory at that place. Now, you might know that, you might want that, that's all perfectly fine. But sometimes it can also point out coding patterns like, did you really mean to create an array here? Could this have been a tuple, for example, which doesn't allocate memory in the same format? So again, the orange is useful to direct your attention to things that you might take a look at and see whether you could improve them. So I want to, in the closing moments here, just demonstrate how you might go about doing some of these things in real world code. So what I'm doing here is I have a VS Code session that's open, and I am going to include this little bit of code here, and I'm going to, what it does basically is it will create a random string of a chosen length. If we make a random string of 8 characters, you can see here, it's generating this random string, and those random characters are chosen from a list that just goes from lowercase a to lowercase z, right? So all these characters are going to be lowercase here. Okay, so now let's check the performance of this code. So this is kind of like a real world performance optimization example here. So I want to do it for a larger amount of code than this. And so I'm going to do this for 10 to the 5th characters. And I don't want to print the result of the string, that would be huge. So you can see it's pretty slow at 0.7 seconds, right? And you can see all these allocations here. These are a bad sign in general, I mean, for code that's this simple. And so those all together might add up saying, maybe I should take a look at the performance of this code. Well, so let's profile it then. So, and here I'm going to be using ProfileView, and that is because it will give me something additionally. So now I'm going to say ProfileView instead of profile SVG. Other than that, it's the same. This will open up a new window on my machine, so it's an interactive window instead of being embedded in the way that it is in Jupyter Notebooks. And if we take a look, you can see there's all this copying that's going on. See this unsafe copy to, it's involving strings somehow. And then there's this big, part of this is substring here. And where this actually comes from is the times operation on this line of code. So here, if I left click on this, you can see it prints down in my REPL. It prints the exact line number and even all the type information for the specific method instance that was being called. If I right click on it, it will actually take me in my editor to that very line of code. So that's a nice convenience. But so we can this helps us figure out what's going on. And what you can see here is that, in terms of what's sort of showing up here, it's all this copying that's going on. And this might be enough to give us a hint. The problem is here, what we're doing is the way we're creating the string is we're starting out with an empty string and we're growing it character by character. But anytime you add one additional character to an old string, it's going to have to copy the old string with a little extra space on the end and add the character. That's kind of a bad design. So let's try to improve that a little bit. I'm going to give this window a little more space here. So instead, what I'm going to do, I'm going to pre-allocate some memory. And I know from lots of usage that Julia allows you to create a string from a vector of uint 8s. And so I'm going to pre-allocate a buffer for this. And so instead of growing it each time, I'm going to simply now stash the random character in a slot. And then at the end, I'm going to return a string out of those chars, okay? So if I go back and I call a random string again, I get a different random string, so it's still working as expected before. If I time it, now let's see, oops, I forgot to load the new code. Okay, so is it still working? It is. How fast is it? Wow, that is a lot faster, right? We've created we've already improved the performance of this code, something close, something like 80 times or something like that, right? So that's already a massive improvement. And we got the information we needed to do this from profiling. So that's really cool. But there's still quite a few allocations here, right? So maybe we should do it again. So let's clear our buffer and collect more data on it. And now, because this runs so fast, I'm going to amp it up a little bit because I need it to run longer to collect good profiling data. And so I went up 100-fold more, more work for it to do. And now if I look at the view, now what do I get? And what you can see here now is, okay, so there's a lot of stuff in the random generation here. There are actually even ways to improve some of this, but we're not going to do that today. And what you can see here is that it's this one line, line 6 is accounting for all the time. If I right click on it here, you can see it's in this place here. But now you might be a little more puzzled. Why is this red? Well, again, that means it's doing runtime dispatch somehow. Why is it doing runtime dispatch? Well, ProfileView has one other feature, which is that it will show you the results of Atcode typed, or actually a special colorized version called Atcode warn type, on the last thing that you clicked on, right? And so here, again, I clicked on this thing here, right? And so if I call at warn time last here, what we're going to see in the output here is a representation. This is, again, that code typed representation that we saw before. You see the cyan markings of all of the types, and helpfully highlighted here in red for you is the part of your code that Julia can't predict a type for. And it's the return value from calling random on this char list. So what's going on here? Well, what we've done in creating this function is we've actually violated what's the first tip on Julia's performance tips page in the manual. I highly recommend, if you're interested in writing performance sensitive code, that you read it. And what the issue basically is that main.charList, which is this thing here, is a global variable, and it's not constant. And since it's not constant, we could change the type at any moment. And so Julia can't create an optimized version of this function with fixed type for charList. It could even actually happen while this code is running, because Julia allows you to have multiple threads going on. And so we could literally change the type from under Juliet while the code is running. So that would be really bad. If it had hardwired in a known type and then that type changed, that would be really problematic, right? And so if you want to fix the performance of this thing, the way you can do it is you can just declare this list constant. And then I would have to restart my session. I'm not, for the interest of time, I'm not going to do that. But this would then get rid of that red, right? This would allow Julia now, since it's constant, it can't change its type or value, then this allows Julia to optimize this function here, and it's going to perform much better. So overall, I think we get, if I remember correctly, something like 300-fold improvement over the changes that we have made here. Okay, so that is the everything that I wanted to mention, I think, as part of this lecture. Just as a quick summary, remember, we've been focusing on the ways in which Julia's performance can be slow, and that's because I want to arm you with the tools that you need to write good, fast code. And you really can do it. And there aren't that many things that you have to know, but you do have to know a few things about a few common gotchas, right? You don't want to use these non-constant global variables. I sort of illustrated that, hinted at that in the last moments here. On the homework, you'll have an opportunity to really play with that yourself. Other tips, not using containers like arrays that have non-concrete types. Those vector of any's were just fatal for our performance. So don't use those poorly typed containers unless you absolutely have to. And that anytime you have performance needs, measuring performance gives you the data that you need in order to optimize your code. Okay, so thank you very much for listening, and we'll see you in the next session.